Alright, so you've already learned all of the content in the one quantitative variable part 1 set of notes. All we have left here is a big example sort of tying everything together. So for this example, we're looking at how long delays are at the Chicago O'Hare Airport. We took a random sample of 87 delayed flights at the O'Hare Airport. Many pieces of information were collected. We collected the length of the delay was one of them, which is measured in minutes. So first off, who is the population? So again, I know sometimes we're going back and doing these old things, but it's still important to remember how specific we might have to be in this example. So for example, you think the fact that we're looking at Chicago O'Hare Airport, is it only going to be good for their airport, or is it going to be good for other airports as well? Well, airports are pretty darn specific, right, and very different depending upon where we are. So we're definitely looking at just Chicago O'Hare's airport. Well, what things are we collecting there? Well, we're looking at the length of the delay on what? On just delayed flights, not all flights, only those that are delayed. So our population is going to be delayed flights at this airport. So for once, we're not actually measuring people here for a change. Right, what's our variable? So what information are we collecting about these flights? The thing we're focused on is the length of their delay. It is measured in minutes, so it is a quantitative variable. Now we're looking at the histogram and summary information to describe our 4 characteristics. If you feel good at StatCrunch, you don't have to watch this part, but I'm just going to show again how to get a histogram and summary statistics from StatCrunch again. So we're going to get into our StatCrunch. We're going to get our data set that we need. Alright, and find our data set here. So they also got the destination, but we're only focusing on the delay. So get our data set loaded. Then in order to get our histogram, we went to Graph, Histogram, selected the variable that we wanted our histogram for, could add a title to it, so we can look at delay length. There's our histogram that we have. To get our summary information, like the mean and the median and the standard deviation, that was stat. Summary stats, we chose a column because our data was organized as a column. Clicked our variable. I went over here and kind of unclicked the stuff we didn't really need and hit compute. So there's how we get that summary information. Now we're being asked to describe the 4 characteristics. So we're talking about shape, outliers, center, and spread. For instance, standard deviation. So if I look at my shape, how would you describe our shape? Well, it's definitely unimodal. This has that one peak to it. It's definitely not symmetric. It's going to be skewed to the right. Alright, are there any outliers? Definitely. This one kind of right over here is an outlier that we have. I can actually figure out its exact value because that would be the maximum. For center, we just need our mean and our median. So our mean is 64.31. The median is 47. And then last, we need that idea of our standard deviation, that we start at the mean and we go out as standard deviation in both directions. Alright, so we subtract it and we add it. Now I have all my information that I'm going to need to put in my paragraph here. So you can go ahead and probably pause it here if you'd like to and try to actually write that little paragraph on your own, and then pause this and then unpause and see if it matches mine. Alright, so hopefully we agree. So when I'm looking at delay lengths of 87 delayed flights at Chicago O'Hare Airport, our data is unimodal and skewed right, with an outlier at 448 minutes. Our mean delay length was 64.31 minutes, with half of the delays being 47 minutes or less. Could have also said half of the delays being 47 minutes or more. The typical delay length was between 6.23 and 122.39 minutes. So I got my shape, got my outlier, got my center, got my standard deviation. So that's what I would be looking for. Next, we're asked if we would use Chebyshev's rule or normal curve rule here. Remember, in order to use the normal curve rule, we need our data to be symmetric and unimodal. That's definitely not true here, so we would use Chebyshev's rule. We are very skewed, right? So we can use Chebyshev's rule only. Then we're asked to create an interval and interpret it. That's 2 standard deviations from the mean. So again, we're going to start at our mean, which is 64.31. And then we'll go 2 standard deviations below and 2 standard deviations above. Alright, our standard deviation is at 58.08. We already have the 1 standard deviation outnumbers from the previous page here. So those are numbers that we get. The first one I want to talk about is actually this negative. Right, there's no way I can have a negative delay length. I'm actually going to stop at the smallest possible value here, which would be 0. Now we'll worry about actually interpreting it. So we're using Chebyshev's rule, 2 standard deviations out. Chebyshev's rule starts with that at least part. So since we're 2 standard deviations out, it's at least 75% of our delayed flights. At Chicago's O'Hare Airport, which is ORD, for those of you that may know that. It's their airport code. Are less than 180.47 minutes, which is roughly 3 hours. Now, how can I interpret it that way to say that they're less than that? Well, right, 0 is the smallest length of a delay anyway, so I really don't need to say between 0 and 180, which you could, and it would be just fine. If they will say it's less than that, that's implying that 0 really is the bottom number there as well. But again, you could put the 0 and that would be fine. Right, in 2010, it was reported that they had a mean delay of 75 minutes and a standard deviation of 48 minutes. That was just reported, so those are just sort of like population numbers here, right? So that wasn't based upon the sample. The mean was 75, the standard deviation is 48. Using this information, note that we sampled 87 days. We're going to find our sampling distribution of the statistic of interest. Let's go ahead and look at our formula sheet, because that, again, will help us. So we're doing the sampling distribution of the mean. And this first box is really in that sampling distribution. So I need to check my conditions, see if my conditions hold, and then I can make my statement that we see here. Alright, so first, checking our conditions. So we need our relatively random and unbiased sample. Didn't really give us a lot on how they got these 87 flights, but at least from what we know, there is nothing bad about it. And then we either need to know that Y is distributed normal, or have a sample of at least 30. So let's talk about this first one again. So if this first one was a true statement, when I look at my graph here, it should look symmetric and bell-shaped. Does this graph look symmetric and bell-shaped? Definitely not. right? We're skewed strongly right here. So that one's definitely not met. Do we have a sample of at least 30? That we do, right? 87 is at least 30. So our conditions are met. So then I can say that my sample mean is approximately distributed normal with a mean of mu, which is our 75. But then I need to find my standard deviation. That's sigma over the square root of n. That's my 48 over the square root of my 87, which is 5.146. And then that number is going to go up here for me. Again, that's all you need for a sampling distribution. We don't need to find a z or anything yet. But now we're going to use that to actually calculate a probability. So the mean from our 87 days is 64.31. Since that was from just our 87 days, that's going to be a sample mean. That's why it's a y-bar. So using our sample distribution that we just found in part F, we want to find the probability of observing a sample mean less than this if nothing had changed. So I'm going to start with drawing my picture. Alright, it's centered at that population mean of 75. I'm going to go out my 3 standard deviations in both directions. For this 5.146 is my standard deviation that I'm going to use. So finding all my numbers along the bottom here. Right, then we take our sample mean that we got, which is our 64.31, which is right in here. And then if it says less than this, we're going to shade to the left. Alright, next we're going to find our z. Looking again on our formula sheet for that. Right, here's our z formula. Y bar minus the mu, sigma over square root of n. So that's what our formula looks like. Again, we already have these numbers. Our y bar was our 64.31. Our mu was our 75. And that standard deviation, that sigma over the square root of n I already found was my 5.146. Right, that's exactly what I did here. Alright, getting that number, our z is going to be negative 2.08. Alright, hopefully that z again makes sense, right? We're a little bit more than 2 standard deviations below our value. Alright, so we take this number to the table, and we should find 0.0188. Do I need to use a rule on that one? Nope, right, remember our table's shaded left, we're shaded left. So that's exactly what I'm going to get for my probability. All the math is done. All we have left to do is the interpretation. So assuming that mu is 75, and if you prefer to write that in words, write that the average delay length is 75 minutes, then the probability of getting a sample value of getting a sample mean less than 64.31 minutes with 87 flights is are 0.0188, or again, if you prefer percentages, 1.88%. Probably again, one of the biggest questions I get asked with the interpretation is, where is that 87 even used? Right, technically that was used in our calculation of that 5.146. Right, that's where that 87 is being used. So if our sample size were to change, our probability would change, which is why I want to include that sample size in my interpretation as well. So I hope I've seen another big example. We'll do another one in class before your quiz, but otherwise hopefully things are beginning to make some sense as well.